and eventually the radial dimension will boil down to a 1D problem, and then you can transfer your knowledge of 1D problems into this. And basically that part of the solution I will not go in full detail, but I will give you some outline of in some special problems, especially the kind of problems which you have seen. For example, the 3D harmonic oscillator. So since you have seen 1D and 2D harmonic oscillator in great detail, I'll not solve the 3D harmonic oscillator, I'll just outline the solution. And again, the 3D infinite well problem, which is again something you have solved the 1D well in great detail, and also kind of know how the 2D well things work. And so I will not solve the full problem, but I will just tell you how the things work, and I will ask you to look it up in Griffiths or Shankar. And then I will also talk about the free particle and finite barrier problem again in a sketchy way. After I build up the generic solution, then what happens when you put these solutions. And then in next class, so that is what will happen in the class today. So I will discuss in great detail about the generic solution, and the special solutions I'll give an outline. And then in the next class I'll go in full detail to discuss the solution of the Coulomb potential or hydrogen atom problem, because we didn't do an analog of that problem in any other dimension. And you will see this problem has some very special features, and also it's one of the most important problem in quantum mechanics, because of the reason that you get very precise numbers by solving that problem. And historically that was the first measurement, the first set of measurements which led people to believe that quantum mechanics is something like that is needed, and it cannot be predicted by classical mechanics. So that's why I will do it in great detail in the next class. But today's class, I will build up the outline of all these 3D problems. So as we realized last time in the previous lecture, that a generic problem in 3D can be written in this form, in central potential problem, where the potential is entirely a function of R. And then we showed by doing the some pure algebra, that algebra for quantum mechanical operators, that this generic momentum square operator can be written as some radial part plus some angular part, which is a full angular momentum operator square by divided by r square. So my whole problem can be written as minus h square by 2m 1 by r square del delta, which is the radial momentum term, plus the entire angular part, the theta phi part, can be compressed inside this. And that is because the system has this kind of a spherical symmetry, plus of course whatever potential you will have, which is again an entirely radial term. And we realize that this problem has this following important, of course it has also this x, y, z, px, py and pz, which are conserved because of the transition symmetry, and all px, py, pz are conserved. But it has also the three more conserved quantity, which is lx, ly and lz, which mutually doesn't commute, but each of them commutes with the Hamiltonian, which is because of the fact that they are constants of motion, and they are this problem has this rotational symmetry. And then we also discussed that there is a Casimir operator, or we will go to the full meaning of this term Casimir operator later. But we at least observe that since these guys are conserved separately, the total angular momentum, which is sum of their square, must be also conserved. And we realize this also commutes with the Hamiltonian, which is also intuitive. But what is not so intuitive, that this guy also commutes with each of these operators separately. So that means this is an operator which commutes with every single other conserved quantities of this Hamiltonian. So now we realize that now we can build up a CSCO for this problem, commuting set of commuting observable, complete set of commuting observable. And then we know that when we define this complete set of commuting observables, we can describe a wave function completely in terms of this or in terms of the eigenvalues of this observable. So in this case, we choose to work with H, Lz and L square. Of course, we realize that we can choose only one of Lx, Ly and Lz because they don't commute with each other. So we choose here, we made a choice, arbitrary choice, and that choice is we choose Lz. It's completely an arbitrary choice. Since all three are symmetric, it's just a convenience. So now we know from our understanding of CSCO that all the eigenstates of the full problem can now be entirely labeled, by this by the eigen values of these three operators. So which means which is something again we learned earlier, that if we have these mutually commuting operators, they will have a common set of eigenstates, and that means you can use the eigenstate level of one of these of each of these operators to completely specify the all the states of this full problem, which is the, and the full problem is the basically the actual problem we want to solve, which is the Hamiltonian eigenvalue problem. Okay, so now, and these numbers, these eigenvalue indices of these operators, they will be called later as the quantum numbers of the problem. So so based on that, let's try to build up the solution. So I first start with the LZ operator. So the LZ operator is xpy minus ypx. If I plug in the polar coordinates, it becomes minus ih bar del phi. Lx operator similarly it becomes something like this, and ly operator becomes something like this, which is not so intuitive, but just 2-3 lines of algebra will give you these forms. So now if I put them together, I will get the L square operator to be this, which is a form we already know, because when we wrote down the full Schrodinger equation, we got this part, which is basically the L square by R square part. So that we observe also by writing down the L operator independently. By starting from this Lx, Ly and Lz, we exactly get this form. So now let's start with this commutation relation, that we notice that these two commute. That means they must have the same set of eigenstates. So I refer to these eigens, and they can be labeled by the eigenvalues of these of these operators individually. So I write the common eigenstate of these two operators as ylm. So ylm is a function of theta and phi, because Lz and Lx and Ly are entirely function of theta and phi. There is no r into this. So I am just constructing the eigenstate and searching for the looking for the eigenstate of this operator. So I'll get this ylm, and I write down the eigenvalue equation for this as mh bar ylm, and write down the eigenvalue equation of this as L into L plus 1 h bar square ylm. So you might wonder that why. So of course, one thing you realize that it must be the h bar presence. If there is h bar present here, there has to be an h bar square here to match the dimension. And also, if this is so, why it is of like an L square form, that you can see very simply, because this operator is a positive definite operator, or if I write in matrix form, it's a positive definite matrix. So if I compute the eigenstate of I calculate the expectation value of this operator, since it's a square operator, it must be always positive or 0 maximum. So that is why I can write the eigenvalues as some square of an integer, but the integer can be anything, but it is square of that. That means it can never be negative, at least. But then you might wonder that why I'm writing instead of L square, when I'm writing it L into L plus 1. So I want you to think that a little bit. Of course, when you solve the full problem, you will see it makes a lot of sense. It helps a lot of at lot of places. But even if you look at just at this equation, you will see that this L square, this quantity has a minima at minus 1/4. So which is something you want to take into account for spin half systems later. And that is why you are writing it in this convenient form, which is L into L plus 1. So that is just a choice. So now we don't know yet what are this M and L. So we just know these are just two numbers. We don't know yet if they are, we have not yet imposed any condition which tells me these are quantized or not. So let's say both of these are some real numbers. That much we know. So now we will try to see what kind of constant it satisfies. So we notice this is again we did this in the 2D problem, that this equation. So this one I write it in the differential equation form. It becomes of this form. So then am I connected or something? Okay, some other random message. So this is the differential equation form. So now this I write down in this like open up this equation and just solve it, and it becomes just this I get as the form of this equation. So ylm must satisfy this in the phi coordinate, must satisfy this because of this equation. But this says nothing about the theta part, the theta part of it. So if I separate this into two parts, the theta part and phi part, the phi part is like that, and the theta part is yet unknown, but it must be a function of this L and M. But I don't know yet the form of it, and for convenience, I just write it as PLM theta. So we'll find out what is PLM theta in a moment. And we also notice that since it's an angular coordinate, it must be like after 2 pi. So this phi coordinate, it must, so phi is, so if I look at this, so So it is like x, y, and z. So this guy is basically this coordinate. So this must this has this 2 pi rotation in this direction. This is theta. This has pi angle at maximum from here to here. So then this must satisfy this constant. So it is again like particle on a circle on this single coordinate. So if it has to satisfy this, it must satisfy this, which implies the m must be an integer. So that is what we get. So we get the constant on the m. So now we want to find about the other part, which is the p part. So now I plug in this form into this L square equation. So now I got this entirely from the LZ equation. I got it entirely from the LZ equation. And now I want to look at the L square equation. So this is the form of the L square operator. This is the form of the L square operator. If I plug in this solution here, and I know this is the eigenvalue equation form, which I wrote down in this form for convenience. So now I plug in this, and I notice that this YLM is of this form, where this part is unknown. So now if I write it down again, I plug in all these forms, I'll get this equation. And this equation will tell me that this part will give me this derivative will give me this m square PLM phi, because this del phi square. And then if I simplify this equation a bit, it looks like this. It looks like this. Now this is yet not very simple. It is like some messy equation in theta phi, and a lot of things are happening here. So what I'll do, I will now do a variable transform to bring this equation into some more familiar and more manageable and more visual form, because these angular coordinates are hard to think in like that. So I make this transformation where x, I replace cos theta by x. So that means that del theta will become s theta del x, and s theta del theta will become -1 minus x squared del x. So if I plug in these two here, I'll get this particular equation. Now here notice that I have separated already the theta and phi part. So this is now a single variable derivative. These del x's are single variable derivative. But for a shorthand, so I should not write it at del x anymore. They are not partial derivative. I should write it as ddx. So just to notice, so I'm using this del x for convenience, but they should be actually dx. But if I write it in this form, it means something else. So there is no shorthand notation for the whole derivative, but there is a shorthand notation for partial derivative, and that is why I kept using that. But notice that this is the more accurate way of writing it. Okay, so now I get this equation, which is a equation in x in terms of x, and then if I rearrange this equation, basically now I divide it by 1 minus x square. So I get this form, and this is a familiar equation. These things are called Legendre equation. So did you do the Legendre equation in math methods?
Yes, sir, we did it.
Oh, great. So I don't need to say anything at all about this. So now, these solutions are this associated Legendre. Again, you get with these by series solution, and they are not polynomials actually. So they are related. So they are expressed in this form, which is a derivative of another polynomial function, and they are called Legendre polynomial function. So now these Legendre polynomial functions are given by this, and these are basically polynomials of degree L. And then so if I plot them, so the p01, the p0 is, of course, it's everything is flat, so it's just a constant. And the p1 is like is x, which is like a line like this. P2 is a parabola. P3 is like some asymmetric curve because it's x cubes, and then you can see this odd even structure is of course there. It is either fully odd or fully even. And then if you, so this is another, so I assume that you don't know this, so that's why I gave this try exercise, which is something very easy for you if you know this. So put m equal to 0, and so if you put m equal to 0, you get this simple equation, which is a very simple second order differential equation. And then you can try to put a series solution into that. So this series solution will, so this is okay, it is still instructive to try, because it gives you the normalization, the condition on L, the quantization on L, just like earlier you got the quantization from while you solved the harmonic oscillator problem and all that. So if you put this series solution into this, you will get this recurrence relation, which connects the ak term and ak plus 2 second term, and it will again, because of this odd even thing, it will have these alternate terms, and then you will get a form like this. And then You also want this guy to terminate at you don't want this guy to be a fully infinite series, because you know that at x equal to plus minus 1, this wave function so that is become in theta coordinate they becomes like 0 and pi, so it must vanish at those points, so it cannot go on to till it cannot blow up to infinity, not vanish, it cannot blow up to infinity, because at x if x is plus minus 1, the series cannot converge, it is like a infinitely oscillating sum. And in that case either an infinite sum or an infinitely oscillating sum. So you cannot let this series go to infinity just like before. There are earlier there was a defined condition, it was diverging in a defined way, this is also diverging but in a different way. So then you want to terminate this series, and the termination condition is equating these two terms, and that gives you the L must be quantized, because the k is of course an integer, so L must be also an integer. So that gives me the L must be 0 1 2 3. But then notice there is also another condition coming. So now we realize that the M has to be integer, the L has to be also an integer, but there is a relation between the L and M because of this form, because the solution of this equation has this mth order derivative on a lth order polynomial. So that will of course vanish if my M mod is greater than L. So that means that there will be no solution if M mod is greater than L. So that imposes the condition that the M mod must be less equal to L. And that implies that for L equal to 0 1 2, so L can be 0 1 2 3 or any integer, but given the L, the M can be only go from minus L to plus L. So that will impose this condition on M, and they are not completely two free or free integers. So now I write down the whole solution. So now I know the theta part and the phi part both, purely by looking at the Lz and L square form of the operator and constructing their common eigenstates, because they are like CSCOs. So now I that will give me this particular form. So this part we already identified and we did not discuss yet this part. This part comes from the normalization. So you can check this by imposing this orthonormality condition, that this YLM theta phi must be orthonormal to this, because and then once you work out this integral, so for that you have to use the orthonormality integrals of Legendre polynomial, you will get this particular p factor. Now also notice that I have written it this in a little funny way to emphasize certain aspects of this solution. I have written it with in terms of this minus 1 to the power m, where this m is basically so m, this solution is for m greater equal to 0, and for m less equal to 0 the solution is related to m greater equal to 0 by this relation. So this is just to emphasize the symmetry of this solution between m and minus m form. So these are historically they are called. So these were first solved for certain for hydrogen atom problem and all. So and there are for spectroscopic reason and various because of some historical reason they are actually called the azimuthal quantum number, and M is called the magnetic quantum number. So they are basically just two eigenstate indices, two quantized eigenstate indices for the Lz and L square operator. Okay, so now that we have this solution, so let's now look at. So now one thing you notice that this part of the solution has is going to stay as it is, because now we are going to discuss all the problems where the potential is of this form, So the potential doesn't have any theta phi dependence. This is symmetric potential. So now let's see what happens to that. So now if I write down the full solution, so it will have some radial part and some theta phi part which we just discussed, and I'm writing it together as a YLM theta phi because they are common eigenstates of L square and Lz operator. And now I want to know this part. In order to know the full solution, I need to know this part. And now if I plug in this form, so I write it as like Ry. So R and Y is just shorthand to that. And I go back to my original Schrodinger equation, stationary Schrodinger equation. I get this form. So it is this is the kinetic term, this is the L square term, this is the V potential term, and this is the energy term. So now if I plug in this, so let me keep the, so this derivative will act only on the R function of R part. So this derivative will act only on here, so I leave out the y part separate in this case. And then it at this step I get rid of the y part, because the y part is not at all doing anything. It is just a constant multiplicative factor, or a multiplicative function. So now I get an entire equation only on the r part, an entire equation. So this is the radial, this is called the radial Schrodinger equation for this problem. And notice that this part is where all the interesting things, or all the variety of these problems, this everything you will, all the variety of solution of this problem will come entirely from this part, because we are dealing with potentials of the form Vr. So the theta phi part will not change at all anywhere, so that they will just stay exactly as it is. And the only part which we will discuss from now onwards is this r part, and this is essentially an 1D problem, and that you can see very easily, because now if I, so this you can already see it is just a one variable function differential equation. So you can equally think it as like a one dimensional Schrodinger equation. You can visualize it in that way. So now let me put a little bit of variable transformation to bring this problem in some more intuitive form. So this RR, I can call it, this thing I can call it an U. So if I call it a U, this equation becomes comes to this form. So this new variable, which is U, is also a function of R. So in terms of this new variable, this differential equation becomes this. And again, this del R is actually a full derivative. So this del R is actually implies ddr. So I'm just writing it as a shorthand. So now you can see that this problem at this level is a basically one dimensional Schrodinger equation problem, just the like kind of problem you already solved in the one dimensional case. Only the main difference is the presence of this term. So the presence of this kind, there was no analog of this term in a generic problem. So if I give you a generic art dependent potential and you want to solve this problem in 3D, you already know the theta phi solution. That will not change, because the Vr is not affecting that part. So the only equation you have to actually solve is this equation. It's a pretty straightforward problem, but it is not just the potential. There will be an extra term which is coming from the theta phi part, but and this is basically an 1 by r squared type term. So this whole thing is a constant integer. For each L it's a fixed constant, but now it is just an extra potential term. You can think it as an extra potential term. So we call it a V effective R. So this is just an and also notice this is a repulsive term, because this just so I will see in a moment that what this term actually is doing. So as you take the R going to zero limit, so this term will start blowing up. So that means it will cost infinitely more energy to come at the origin. So that means this term will actually prevent you from going to the origin. So that's why it's like a repulsive term, and it's of course a positive potential. So if you calculate the force is negative, and that implies it's a repulsive type of term. And you immediately can see that this will also tell you that since you cannot reach to the origin, it's an energetically impossible the thing. It is like a infinite. If I plot this potential for a generic Br, so this is some specific Br. If I take a generic Br, I don't know what is the Br. At least at the origin, it is going to blow up, whatever happens in the rest of the space.
Sir, excuse me, sir.
Yeah.
So the second graph that you draw, yeah, of VR equals to A by R square plus B by R,
Hmm.
yeah, will that have the rise after having the lowest point? Will that rise up, or will it go asymptotic at R goes to infinity?
Infinity.
Yeah,
So
yeah,
what happens at R goes to infinity?
yeah.
Mhm. Yeah, at R goes to infinity, this term will dominate, right? So the question
Yes,
is, does
sir.
it have a minima?
Yeah, yeah, yeah,
So
yeah.
let's take that.
Like proper distinct minima where if I draw a, yeah, line
Yeah, I think
parallel
it will
to,
have, but let me
no,
see. Let me
no,
check
sir.
that.
I'm saying that if you have a parallel, yeah, line across V. Oh yeah, parallel to R. Will that
minus
line cut
3b
into
by
2 points?
r square, right? Like minus 3b, sorry, 2b by r square minus b by r 2a by r cube b by r square. So this is the dvdr. So if I put it to be 0, what will I get? So if I put it to be 0, I get some solution, right? So I get r cube here and r square here. So I get br to be minus a. So r gets to be minus a by b. Is that right?
Yes.
Yeah. So it will have some minima, right?
Yes, a
Or
minimum.
at least some.
Yeah, yeah, minima will be there. But the thing is that while if I draw, like in the first case, what happens is like the lowest point of energy is at some particular R, right?
Hmm.
So if I draw a line parallel to
Yeah. So
R
this
axis,
also has a particular r, right?
yes, yes,
There
sir,
is a
yes, sir.
particular r naught where it is minima. That means it must rise in both sides.
Yes, sir. But the thing is that if I draw, what you say, draw a line parallel to R axis, yeah,
Hmm.
parallel to R axis in the first case, it will
Yes.
distinctively, yeah, yes, sir. So it will distinctively cut into 2 points.
Yes.
Yes, sir. Like 1 point here and 1 point here.
Yes.
Will that happen in this case? That's what I'm saying.
Yeah. You can also draw a line like this, right?
Yes, sir. But if A and B, like as Aradhya said,
Sorry. What did you say? I have to check that.
like Aradhya said that A and B both have to be positive. That's obviously there because that's the difference that's making. But the thing is that, like yesterday I drew this graph, like this kind of graph, like one
Hmm.
by R square plus one by R. It was going asymptotic towards the R. That's why I'm asking if you can do plot it anywhere, like one by x square plus one by x. The positive quadrant would be like the the thing will
Okay, I
go
have to check it
asymptotic to
then.
R.
Yeah, so I think I
Yes,
I have to check it. I don't.
yes, sir.
Maybe I didn't. I was not very careful while I draw it. So
Yes,
I have to
yes, sir.
check this plot. So okay, that could be actually a nice exercise. So the
Yeah.
point of, so let me tell you what is the motivation why I was doing these two plots. So let's say I have a particular potential which is ar square minus br, or I have a particular potential. Oh, I see. I know why I did this plot. I think I know, because I am plotting the, if for this br I am plotting the b effective r. Okay, so the
Yes, sir.
b effective r has this part also, this some additional 1 by r square term. Okay, so now
Yeah.
this additional 1 by r square, and yeah, I have to look into it. Okay, I'm confused. I will
Yes,
just
sir.
plot it maybe. So one of them will be asymptotic, another of
Yes,
them will be
yes, sir. Like maybe at the end of the class, I can show you what I
yeah.
did.
So it is basically just so the point is here to point out the difference between an attractive and repulsive potential. So the attractive potential, which is of this form, so that will allow a bound state. So that is the whole point. And this repulsive potential will let the particle fly to infinity. So that is what I wanted to emphasize here. So anyway, so the main point here I wanted to show that because of this 1 by r squared term, so if you are dealing with a regular problem with some without any extra weirdness or like delta function or anything, then you expect that this r square part is the diverging term at r going to 0 limit. So that means it will put an infinite uphill potential at when the particle will approach to r going to 0, and that will cause us to demand that as r goes to 0, the psi r must go towards 0. So this is not very weird demand, because if you look at the equivalent so normally when we solve problem of particle on a line, we go from minus infinity to plus infinity, but here instead we are going from 0 to r. So in the radial, so that is why even though it looks like a 1D problem, it's actually on the half line in that sense. So so the 0 and r are the two extreme points, and this tells you it cannot go to 0 at least, because of the presence of this term which is coming from the theta phi part. So this is one point you have to keep in mind when you visualize this problem as a 1D problem. That's one crucial difference from the 1D problem. And another thing, important thing to notice, is that this radial equation is m independent. It doesn't matter what the m is. It's only as the L part. So now I can write down the solution of this radial part as E and L. So I just keep two indices, and the radial and the angular part is L and M. So look up into this. So try to play with a little bit of some potential. So this is attractive potential. This is a repulsive potential. Look at some other potentials. So try to draw the effective potential, and then you know what kind of equivalent 1D problem it represents, and what kind of property this 1D problem will have, that you know from your experience of solving various 1D problems. So that is the purpose of this exercise. So now so notice that this part is this part is called the spherical harmonics, because they are eigen solutions of L square and Lz, and they form a complete set of states or complete set of functions. So that means any function in this theta phi coordinate can be written as a linear superposition of these functions. So this is the special importance of these spherical coordinates. And this part, which is actually the R part, and we wrote that R as that part as u is small r times the capital R function. So the actual R part is basically u by R form, and it will have a energy index, or E in, which is the eigenvalue index, because it's the E eigenvalue equation like this. But I don't know yet what is that. It is quantized or not. That also, of course, depends on the problem. It's a bound state, it will be quantized. Not bound state, it won't be quantized. So that's why I keep the index E. And then there will be an angular momentum component, or a L component. So I have not used the word angular momentum extensively. So let's just call it some azimuthal quantum number L. So that will be the full form of my solution. And again, I can check this normalization of this by checking it by putting it these two parts and using the normalization condition of the spherical harmonics separately. So then I have to satisfy this UEL as like, again, just like a 1D problem, but importantly on half line, on the 0 to infinity. So that is the main difference from visualizing it as a 1D problem. It's a half line problem and it blows up at origin. So these 2 points you have to remember. So now also notice that this condition, so normally when we put this condition that is some part of the solution you put it to 0, and that usually comes from the problem of normalization. So notice that this problem is not coming from normalization, it is just coming from the fact that it's an infinite potential, that point. So now let's try to see that this is a quick check, and this is you can do just by putting it to be some constant, this part, and see that if what happens if it is not 0, if by chance this part is not 0. So let's take the condition for L equal to 0. So put L equal to 0, that means M is of course 0. So then the full solution will become C y00 by R, and y00 is 1, that is some constant, not 1. So it is C prime by R. So I know this is the solution. So now if I put this solution, you know this solution cannot be the solution of the problem, because you have done this kind of problem, I think, for electrodynamics, because if you have a point charge, if you solve the Laplace equation, you get a potential for that potential, which is 1 by R potential, you get this the point charge will appear as a delta function. So the delta square, so in the Schrodinger equation you have this delta square. So that when you apply the Laplacian on this function, on this, if your f function is of this form, if you apply the Laplacian, you will get a delta function. So that delta function, it's a 3-dimensional delta function, and this cannot exist, because that means there is some infinity in your problem. And to compensate that delta function, you need another delta function somewhere else, and that delta function is not there, because your VR is neither so your VR is some nicely behaving function, and it has this L square by R square order term with some constant. So none of them are delta functions, so that means this is an inconsistent situation. So that it is just a quick indirect check to show that if I put this u to be non-zero at R going to 0 limit, that will give you a solution which is not a solution of the Schrodinger equation. But except the case if there is actually a delta function in the problem, which means the potential itself is a delta function, and that problem is very non-trivial to solve, and it has a lot of issue in this problem, and we will probably not even discuss that within the domain of this course, but we can talk about it separately, because it turns out that you need to use a technique called renormalization and what is the other thing called the regularization in order to deal with a delta function in 3D. But if in a normal regular problem you don't have a delta function, and then no infinity in the problem, then it will lead, this Laplacian will give you an infinity, and that is an inconsistency. That's why it must satisfy this limit. And if you want to think it physically, even without going into any mathematical mumbo jumbo, you can think it, because there is an infinite potential. If the potential is going uphill infinite, it cannot go there. So now let's take the other limiting condition. The other limiting condition is we want to know what happens at r going to infinity. So now let's talk about a potential where the VR is going to 0 as the r is greater than r0, which is typically what happens in most, in a large number of potential, because we know in many potentials it is like a finite region, and outside this is 0. So then if that is the case, then it must and if it satisfies at least this condition, even if it is not actually 0, it is, if it is growing slower than r itself, so then at least if it is satisfying a condition like this, then you can write down the r going to infinity Schrodinger equation for the radial coordinate. This, like, since it rained on Diwali, people had the stock of their crackers, and they will probably keep busting it till like infinity until they finish all their crackers. It's so annoying. Anyways, so now we will look at this solution at the r going to infinity limit. So if this condition is satisfied, that means this term, this VR term, will be dropped out. And if the VR term is dropped out, then I have a very simple equation to solve. And we have solved this equation for a free particle already in earlier example. So I can just write this equation in this form, and notice it will have these two types of solution: the bound state solution, which are basically for e less than 0, this thing is an exponentially decaying solution, and if e is greater than 0, it is an oscillating harmonic solution. And then if I plot these two cases, so one case, so let's look at the bound state. So e get less than 0, so we already established that the u part must go to 0 at origin, and then we realize this u is exponentially decaying to, so it must reach to origin somehow, and psi must be continuous everywhere. So psi must be continuous everywhere, so that means it must be connected by some continuous manner to u going to 0. And in the u going to and the r going to infinity limit, we also have shown that this thing exponentially decays. So then something can happen in the middle that depends on the details of the potential. It can have no node or one node or something. So this is also an instructive exercise. So if you know the solution at the 0 and infinity, can you guess the full solution of the problem without actually solving it? So that depends on the, because it's an effectively 1D problem, so you know, you can guess the solution, the form of the solution in that 1D problem. So this is again, I like you to try a little bit and play around with some potential and see what happens without actually solving. And then what happens to the stationary state? The stationary state solution again tells you it must be 0 at this point, and here it is oscillatory at the r going to infinity limit, and somehow it will be connected in the middle. So that again you can try to guess what it will be for a given type of potential and all that. So that tells you, you can say a lot of things about this problem without actually solving it, because of this nice structure of the problem and this nice 1D like character of this. But also one must keep in mind these two critical difference from an actual 1D problem, because this problem is not really an actual 1D problem, it just looks like a 1D problem. So now there is one very special case which I want you to think, and I will discuss it tomorrow. It will appear in the case of hydrogen atom problem. What if the potential is of the form of 1 by r? So in that case, this guy is not, this whole condition is not valid. So if the VR is 1 by r, or at least slower than 1 by r, that means this guy is not going to 0 at r going to infinity. So then what to do? So then you can show that this problem will have a power law solution. So it will have a power law prefactor solution. I want you to think a little bit about it, and try to give an argument that why it must be of that form without solving the full problem. And then we'll see it again in the tomorrow when we'll solve actually the problem. So that is these are all the possibilities. And then we will now look into the spectrum of the problem based on this possibility. So now let's see if I have a bound state. So that means if I satisfy this condition, if I have a bound state, then I expect that this the energy must have a must be a multiple of an integer n, and we'll solve specific example of that. And then for each so notice that when I look at this effective problem, so this effective problem for each value of L, so the L can be, L is an integer which goes from 0 to infinity, and for each value of L, the M can be minus L to plus L, again as an integer. So for each L, it's a separate potential problem. Also, like qualitatively same, but quantitatively because of this number is changing, is a separate problem. So then you expect for each L, you are solving a different problem, and then this problem has its own set of n, like so own set of bound state energy levels. So if even if you don't know anything more about the problem, you can expect, you can sketch the structure of the problem to be like that. So if I plot the energy in this direction and plot the L in this direction, for L equal to 0, I will expect the problem will have this kind of a so n will change. So n will change from, oh my god, they are now bursting this series crackers. I don't know what it is called, the one which burst in a long chain. Okay, so now the n will go from it totally disrupts my concentration. So the n will go like 0, 1, 2, 3 like this, and they are not did not to be equidistant. And I just drew it like that as if it looks like equidistant, but I'll show you in a moment. Of course, you know this is an effective 1D problem. If it is even a square root, it won't be equidistant. So you will get this solution for the n part. And again, you notice that this is totally non-degenerate because L equal to 0 means the m has to be 0. But if my L is 1, so then I again I can draw these lines. So then it becomes 0, 1, 1, 1, 2, 1. And this each of these lines are doubly degenerate. So there are two lines basically. Because if L is 1, the M, no, not triply degenerate, because then the M can be minus 1, 0, plus 1. So because there are 2L plus 1 level degeneracy for each level, and so on. So similarly, you can draw the whole spectrum of this problem without actually even solving the problem. I mean, a qualitative picture, but now I'll see how will I draw the actual problems, the full picture. So now we are almost done with all the outline of the all the kind of descriptions. So now I will discuss some specific examples. So there are mainly four types of problem we will do in this course, and that's these four types of problem I want you to fully master and think about it, even though I will not fully solve all of them. So I will discuss. So today I will give an outline of the problem of free particle, which is a very simple problem. That means the Vr is zero. The Vr is zero, and then or the Vr is some constant, like it is like constant everywhere. And then I will talk about the spherical well, which means it is it can be either Vr equal to is some finite number in a confined domain. So it is like okay, this is not a right picture. In some confined domain, Vr is finite, or the Vr is zero in some finite domain and infinite everywhere else. So these are these two: infinite well or spherical barrier or spherical well problem. So this we'll also discuss. We'll discuss also the isotropic harmonic oscillator, where Vr is like half m omega square r square. These are all all these. So the spherical infinite well and the harmonic oscillator are basically same category of problem, because for both of them this problem the potential goes to infinity as r going to infinity. Oh, distraction again, somebody is knocking me. Just a moment, I just want to check who is knocking. Sorry about that. Sorry, it was completely a random distraction. Is my screen visible, or I somehow disabled the screen? Hello? Am I audible and visible?
Now it's fine.
Yes, sir.
Okay, sorry. Okay, so now we will talk about these three class of problems, and tomorrow I will go in great detail about this Coulomb potential. Sorry, which is basically the hydrogen atom problem. And this is, of course, a very historically important problem, because this hydrogen atom problem allows you to calculate the energy levels of a atom or a bound electron system. And that was historically the first class of problems which was experimentally people detected the transition line of atoms, and then realized that there is these things are quantized, which cannot happen at all classically. Then they required the need of quantum mechanics, and there is an unprecedented quality of prediction of quantum mechanics you will see there. So in this when we will do more about this course. What is the comment? Okay, some earlier comment it is probably.
Yes, sir. Yes.
Okay, so we will see that we will not do all of this in this course, but later we will see there are these fine structure, hyper fine structures, and all those things, relativistic correction. And actually it turns out that the quantum mechanics can predict like 16 place after decimal of this. Like this is like no theory is probably tested of that kind of precision and accuracy. So that's the unprecedented success of quantum mechanics, which you can predict the experiment and match with it. And that is why this problem is so important. And all other problems are, of course, in nature there is no perfect simple harmonic oscillator, there is no perfect spherical well, there is no perfect free particle, all those issues are there. But there is an almost perfect Coulomb potential, and that's why this problem, the prediction between theory and model and experiment is unprecedented. So that's why it's such an important problem. And usually if you go to any book, they make a super big deal out of it. They will spend almost an entire chapter on this problem. But what I want you to realize that these problems are belong to a family of problems, where which one can solve very sequentially and step by step, and build up a lot of intuitive idea. And it became important because it is one lucky situation where a system in nature actually is resembles the model you are making. But even when it is not true, these problems are all of these problems teach you a lot about the physical system, and give you a lot of nice idea and accurate physical representation. And then there is another problem, which is the delta function potential, the 3D delta function potential problem. This is something we will not do. And this is, there is also another problem, which is 1 by r square minus 1 by r square potential, which is again these two problems has a issue of regularization and renormalization. So you need to use this idea of regularization and renormalization, which is something we will not do in this course, but these are very rich problems on their own. Okay, so let's now discuss a little bit about these three problems. So first, the free particle problem. The free particle problem is a little different from the actual free particle problem in 1D, of course, because of this extra term in the radial coordinate. So this is the equation which you have to solve in order to know the free particle problem. So now I'll do some so I will just write it in a nice form. So I write the k square equal to 2. So I change the mass to mu again here, because there is this azimuth, this m quantum number. So that's why I changed it to be mu. So then this equation becomes d2 dr2 plus k square minus ll plus 1 by r square u. And then if I plug in the solution, that rho equal to kr, so then I mean not plug in the solution, I just do a variable transformation to make the solution looks a little more neat. So if I do that, so this becomes it's just a scaling transformation. The k is a constant, k square is a constant. So this equation takes this form. So this is a familiar form. This almost looks like the harmonic oscillator or any one-dimensional oscillator problem, except instead of rho square, this is 1 by rho square. and this is a standard solution. Actually, these things are this is a standard well known differential equation, and these solutions are called spherical Bessel function. So if you might have seen this in the mathematical methods course or some other course in some other form, but even if you have not, it is just a standard solution. So then my UEL is of the form C rho JL rho, and then if I go back to the to the r coordinate, it becomes JL KR YLM theta phi. So this is my full solution of the problem, and then I can plot it again. So you can look up the plots of this function in the free particle, in the free particle basis. And then, as you expect, that this must be a sinusoidal and oscillatory solution everywhere, because if free particle, there is no bound state. So this solution actually in the r going to infinity, if you take the r going to infinity limit, the solution will take this form. This again, you can guess that this has to be a sinusoidal form, because this guy has to vanish at the origin. So that is why it's a sinusoidal form. And then one more, a little bit of exercise you can do. Then now you put a finite potential at some region in space, a finite potential like this. So only in the r coordinate, and then you can show that the r going to infinity solution will have a extra term, energy dependent term, which is basically that will come if you put a extra v here, and that extra v will show up here, and that and it will be a v and e dependent term, because this k square will contain the v. And then you can show that this will have an extra phase into this solution at r going to infinity. Now this is a very useful and interesting exercise. I strongly suggest you to do that, because this has a very strong physical consequence, because it tells you, if you just look at the wave function, so there is some scattering happened, or the wave function have encountered some potential at the origin, or at some finite region of space. But if you look at the wave function at infinite, at r going to infinity limit, these are both r going to infinity solution, then that contains this information, that so if it have not encountered any potential anywhere, then the wave function will have this form. But if it encountered a potential somewhere, it will have this form. So that means, just by looking at the scattered wave function, or just the wave function at infinity, you know what happened, or you know information about the system in some finite localized region far away from where you are observing. And that is the heart of all the scattering experiment. All the scattering experiment one do in high energy and condensed matter physics, it tells you what happened in a finite region of space, in a finite potential, where you actually observe a particle far away from the potential, and it still carries the information about what happened in a finite region of space. So that is why it is a very interesting problem. So now I want you to also look at the particle in an infinite well, which is a problem which is fully worked out in Griffith as a example problem. So the problem is, again, there is a finite spherical region where the VR is 0 and it is infinite elsewhere. So then if I plug in this potential, the in the region where the solution is 0, the equation will look like this, which is basically exactly like the r free particle, but it must satisfy this boundary condition, that it must be 0 at all the point on the sphere radius. So the L equal to 0 solution, from here you can work out again. It is exactly like the infinite well problem. You will get the except there is a little difference, because it's a spherical, it's a circular well, I would say. Well, it's yeah, in it's not a circular well, because in 1D it is basically just a 0 to L. You are effectively solving a problem in infinite well, basically. So the radial part will have this again quantized energies, which are basically just like the square well problem. But the wave function will have again the square well like structure, except there is a 1 by r part, because owing to the fact this is actually a 3D problem. So now if I solve this again, if I solve this all the n's for, I'll get this. If I plot it for L equal to 0, I'll get these lines. So they are not equidistant, because they are n square gapped. And then if L is not equal to 0, so you can show that this, again, a very simple exercise. You can show that the solution will be not of this form but of this form, will have a L dependence. So this is a spherical Bayesian function. This is called a spherical Newman function. And again, if you look at the energy levels at L equal to 1 and L equal to 2, you can again draw it to be this kind of with some unequal spacing and gap. So this is another very instructive exercise and very simple exercise which you can do. And finally, the particle in a 3D harmonic oscillator. This is again, you can guess what will happen, because effectively it will boil. You already know that if I solve it in XYZ coordinate, it will have this kind of energy level nx, ly, nz plus 3 by 2 is h cut by omega. um, h cut omega. So if I look at but there is an important difference, that each of these levels are now degenerate even at the n space. So this thing you can write it total like n plus 3 by 2 some integer h cut omega. So because of the spherical symmetry, each of these levels themselves are degenerate even at L equal to 0 and L equal to 1 and so on. And on top of that, they have the degeneracy, which is because of the m's. So this degeneracy plus the 12 plus 1 degeneracy, there will be a huge degeneracy in this problem, and these levels will be equally gapped. So if you do a spectroscopic measurement, like if the atom is going, the system is going from one level to another, this level to another, there will be just one frequency, because all the levels are equally gapped. So a neighboring transition will just give you one spectral line. So that is the interesting characteristic of this problem. So these are the three problems I want you to play with and develop some intuition about. And then what I'll do tomorrow is I will go in details about the Coulomb potential problem. And that will be basically it about the wave function direction of this problem. And then next week I will go to the algebraic solution of this problem, which is doing the full from the bracket solution and algebraic ladder operator point of view. We'll develop this whole rotation symmetry and their angular momentum algebra. So that is basically the plan for the rest of the 2 weeks of this course. And that's all about today. Okay, so that's all. Is there questions we can discuss?
Yeah, yes, sir. The potential thing that you were talking about.
Yes,
Yeah, yes, sir. So if we draw, like, can I show you something?
sure.
Sir, like, I have to present it.
Yeah. Oh, so I have to
Yeah,
stop
yeah,
presenting. Okay.
yeah, yeah. If it is over, then yeah, yeah. Wait a second, sir.
So let me also plot it. So
Sir, can you see it? Can you see this?
I can
Sir,
see your screen. Yes.
yeah, yeah, yeah. Okay, okay, sir.
Fx
So
equal to 1 by x
yes,
plus
sir. So
1 by x square, right? So that
yes, sir.
was
So, sir, can you see my V effective? Like it is on the form of 1 by x square plus 1 by x.
hmm.
Okay. And I draw this one. So I get this kind of thing. It's going asymptotic. Okay.
So 1 by x square. So what were the
Wha-
two things? Let me just
1 by x square plus 1 by x plus 1 by x. So what is happening is here is like this. So if I draw, yeah, like draw a simple graph like 1 by x square plus plus 1 by x. Okay, so there is a minima, but it is in the negative quadrant for x. Okay, and since we are taking x as the radius from the center, so it can't be negative. So that's why I'm saying, like, can we take, like, can we have a negative in the case of 1 by x square plus 1 by x, like an acceptable solution? This is what we will actually get. But in the second case, when the potential is actually attractive, what we get is this minus 1 by x. We get a minima in the first and fourth quadrant only, means the acceptable value of x. The x is greater than 0. And since x we take usually the radius in the polar coordinates, it's just the positive area solution we are
So
taking.
which one is what? I didn't
So
get
so
it.
so the green. So can you see it here? So,
Yes.
yeah, so the blue one, you can see this blue line. Blue line is this one. So
Blue
blue
line is
line
which
is,
one?
yeah, blue line
The
is
plus.
this. Yeah. I have
The
written the equation. I have written the equation out here too. Like blue is this 1 plus x square plus 1 by x. This is the blue one. So the blue one is basically the attractive attractive potential, which is getting a minima at the negative quadrant of X. That's what
Repulsive.
yeah, yeah.
Blue is repulsive.
Blue is re- blue is repulsive. What did I say? Attractive. I'm sorry. Yeah, yeah.
So I'm just
So
also plotting it just to see.
yes, sir. So this is the thing that I'm saying.
So
So as Aradhya also pointed out, like the minima will be there, but in the negative quadrant. Even if you do it by hand, you can see that how is
yeah,
it
but that
possible.
is not a, so yeah, so one
So
case it will, so what is the mm, one case when the particle is flying to infinity, which is basically
yes,
the blue line,
yes,
and
sir.
blue
If
line is
if we take
a
only the
repulsive potential. Yes.
yes, sir. If we take the solution of only positive x, and since we
Yeah.
usually take like this entire thing in what you say, like x as the distance from the origin
Hmm.
in the polar coordinates, only
Yes.
we only take the positive values of x. That's why we
Yes. Yes.
can't have a acceptable solution of repulsive 1 by x thing.
Yeah. So that
That's
is,
what I wanted to say.
I
But
see. Okay.
yeah, but the thing is that if I plotted something else, so for 1 by x square, but if you have inverse square law, okay, in
Hmm.
both the case, repulsive and attractive, we
Hmm.
can have we can have bound states,
No, what do you
acceptable
mean
bound state.
by, yeah? So no. How can you have a acceptable bound state?
Because yes, in case of inverse square law, in
No,
case
what
of
do you mean by inverse square law? Inverse square
inverse square
potential.
law, yes, sir,
Right?
inverse square,
Inverse
yeah,
square
yeah.
potential is not has many other problems. So
Yeah,
inverse square potential, I'm not talking. I'm talking about Coulomb type potential.
yes,
So
so Coulomb
so
type.
when you use the word
Coulomb type is
inverse square law, it means
influence.
inverse square in force, not potential, right?
Yes, sir. Yes, sir. Sorry, sorry. Yeah, in potentials,
Yeah,
in force. Yes, sir.
in
Yes, sir. In
force. So
gravity.
that
Yeah,
means
yeah,
in
yeah. In
potential
force.
it is
Yeah, yeah,
one
yeah.
by x.
Yeah, yeah. In potential, it's 1 by x. Yes, sir.
So if you want, so that is what I wanted to say. If you allow a inverse square potential,
Hmm.
that problem is a nasty problem. It has, as I said, it has this renormalization and regularization, all these things you have to do that.
Okay, sir. Okay,
It
sir. Okay,
turns
sir.
out that problem doesn't have a bound state. It's a well, sorry, it has infinitely many bound state. It's a bottomless potential, and if it is attractive, so it is a very interesting problem on its own. And it turns, as I mentioned this again in some
Which
class.
case, sir? Which case did you mention? Could
Yeah,
you
it's
repeat?
it's an inverse square potential, not inverse square force.
Oh, okay, okay, okay. Like 1 by x,
Yes, 1 by
1 by
x
x
square
is
potential. Yeah, so these are called conformal symmetric problem. This has
okay, okay,
some certain structure called conformal symmetric, and they're prototype of the scale invariant problem. So they don't have a scale. So the particle,
okay, okay.
it is not even stable. And there is a paper by Griffiths, the book author Griffiths. There are actually two famous Griffiths. This is the book Griffiths, the guy who wrote the book. So he has a paper on this potential, a whole paper. It is not even a textbook material, it's a paper material. I can send you that. It's
Yes, sir.
very instructive to solve that problem, because you will learn some very fancy techniques which are usually used in advanced level QFT. So it is not a very weird technique. There are some you have to do some massaging with the mathematical solution and do something called renormalization to deal with the infinities in the problem.
Okay, so
So,
if the potential goes by 1 by x square, then only
yes,
the
that
weird terms
problem is,
comes up.
yes, that problem has many weird problem issues, and it's a very rich problem. And it is also similar rich thing happens in the delta function potential in 3D. That's why I didn't discuss it. Both of these problems are very weird problems.
Okay, sir, I
You
got it,
require a
sir.
lot of technical things. But the
Mm-hmm.
inverse square potential, which is the inverse square force,
Like
what
1 by
1 by
r. Yeah, yeah, yeah. The
1 by
potential
r,
goes
that
to 1
problem
by
is
r.
simple. That's a
Yeah,
textbook
yeah,
problem,
yeah,
and
yeah, yeah.
that is what we will solve in next class. But it is also very instructive to look into this intuitive solution, which means in the I discussed that the problem where r goes to 0, in that problem we will have this for that problem you can build up the solution at r going to infinity and r going to 0. If you know the solution at r going to infinity and 0, you can guess what happens in between.
Mm-hmm.
You can
Yes, sir.
apply node theorem and all that, just like a 1D problem.
Mm-hmm.
But when that doesn't happen, then also you can say a lot of things intuitively. So this thing is actually discussed in this book of Shankar. So you can look it up, and I'll also discuss it tomorrow,
Mm,
which is where this RVR condition is not satisfied. Yeah,
okay, sir. And could you send us the paper that you were talking
yeah,
about? Because
I'll
it's
add
been
these two papers
interesting.
in Piazza. So there
Yes,
are
sir.
two papers,
So
one
this
on this delta function, another on this inverse square. Yeah.
this inverse square potential is basically just a like very similar to the potential of just a dipole, right? Why is it so complicated?
No, dipole is 1
Like,
by r cube, right? Or 1 by r to the
Dipole,
no, it is one
dipole
by
is
r
one.
square.
Dipole is one by r
1 by r
square.
square.
Yeah, this problem is complicated because as it has this what will I say, it has this scale invariant. So again, I have to explain you what is scale invariance. So you have to multiply, if you multiply the space and time coordinate by a scale factor, if you,
E-
it turns out that problem remains invariant. That is no, that means that problem doesn't have a scale. For example, the harmonic oscillator problem has a scale, which means you cannot multiply the space and time arbitrarily by n factor. If you do, then the problem will, dimension mismatch will happen, and that will also, that means there is a finite energy scale. This implies a finite energy scale. This problem doesn't have that property, so it is scale invariant. Again, it requires a little, it might not make full sense to you because there is a symmetrical conformal symmetry. So the conformal
Does that mean
symmetry, huh?
does that mean anything? Does that mean anything in a classical sense?
Does that no,
Mean
classically it is
anything?
not that problematic. In
So
quantum mechanics,
classically also it is a bit problematic because what I
right?
was trying to do was, yeah, using the Bertalan's theorem, I tried to solve the gravitation problem. Okay,
Hmm.
if I apply that same theory with, yeah, what you say, with a potential called x square for
Hmm.
harmonic oscillator, we can't do it. So we have to do it a bit different. Okay, so I
Hmm.
was getting one weird problem with the powers of r basically. So if it is negative, we'll get some answer. If it is positive, we'll get some
Yeah, so
answer.
this, so
It
classical
was
one I have
real.
to think a bit, but this
Yeah, yeah,
problem
yeah.
is a very weird
But
problem. That is
yes,
what I.
sir. Like what I'm saying is that it will be. I think so. It will be a bit, yeah, non-trivial for even the classical way because we are
Okay,
getting
I have to
lucky.
think a
Yeah,
bit.
yeah, yeah. Yeah, because in the case of gravitation, we actually get lucky. The
Yeah,
solution is
so
like really
actually you
happy,
can
happy.
ask this question, that if I have a 1 by r to the power alpha potential,
Yes,
and in a and it depends a lot on the time. By the way, this is all about the 1D. I'm talking about a pure 1D case. So if I have a, and of course this is all 1D because a radial coordinate, it's all a 1D problem, entirely 1D problem. So if I have a 1 by r to the power alpha, at what point of alpha things will get weird? So this is a very interesting question because there is a this calls a critical dimension. So depending on the, so this alpha, what value of alpha will make things blow up at the origin, and that cannot be recovered by any integral. So that is an interesting
we
question.
have we have some like selective, what you say, selective cases given, like ready-made selective cases. So if it says that if
Yeah,
the potential,
because these
yeah, yeah,
problems
but
are important. That's why they are given to you. But
yeah,
these
yeah,
weird
yeah.
problems are also important. They appear in various many body physics problems. They
Okay,
appear in some very effective problems. And actually, these conformal symmetric problems are related to, as I was saying, there is something called ADS CFT correspondence. So that allows you to look at this unstable solution. So you look at the CFTs, and there is some gravity black hole dual to those problems. There is a very rich physics behind those problems. But right now, so I'll send you those two papers. Don't get into all these weird things, but just look at these two papers just to see, appreciate all the things happening in this inverse one by. And you are saying why the dipole problem doesn't have that problem, which is 1 by r cube problem. I have to think a bit. I don't know if that will appear. So if I do an
No,
r cube
so
problem,
we don't know
dipole
like
is also 1 by r square. Like
no,
the
yeah,
no,
yeah,
potential is
is it?
still 1 by r square.
Okay, then it is
Yeah.
probably the dipole problem. It is the dipole problem.
yeah, but we are, yeah, like dipole problem, we didn't have it because we were not trying to find the bound state of a
Yeah,
dipole.
if you are, for
Yeah,
example, trying to
yeah, we
find,
just found the potential,
yeah,
right,
then
in
you will also land
electrodynamic.
on this problem.
Yeah,
No,
yeah, we
in case you want to do so, then you will also see that same problem. If you have a
mm,
field or created by a dipole,
mhm.
then yes, then you will also find this problem. So then, yeah, so this problem has a lot of also. but I have to, why didn't I see this discussion anywhere? Okay, I have to think or look it up. That why people don't, because dipole problem is much more common, but this that conformal problem is not so common. They are a very academic problem, not a very, I mean, they are a real world problem in some very special cases. So that is what one thing you have to understand, that most of the models you study doesn't exist in reality. What exists in reality is something very close to that. Even a circle is a idealization. There is a very interesting question, that is there any circle in nature actually? So nobody, apparently there is no perfect circle unless it is human made. So it is like that. So all these problem are very idealizations, except this Coulomb problem. These also idealization, but they're very close. That's almost exactly the same problem, and that is why this problem is so important. But in other problems, you may or may not find it a real counterpart for it, but you can find something very close. Even that is cool enough. So that will happen all the time. Yeah, I'll send you this problem. This is a very but what I want you to do, like, of course you will do look at the solutions in the books, and the books has everything, all the solutions. But what I want you to stare at the problems and try to build up a physical intuition. Like these things you want to, you won't be able to carry the solution in your head all the time. You will forget the solution, but these intuitions you will carry in your head all the time, like this: taking the zero limit, taking the infinity limit, what will be the shape of the problem. If you know it infinity and zero, can you guess what happens in the middle? So practice those things a little bit. So spend time with the problem, then this intuition will develop. And the actual solution, you look it up, do it once maybe, but then you will forget it anyways. That is guaranteed. So but what you will remember is these limiting cases and these physical pictures. Okay, so that is all.
And one more question, sir.
Hmm,
Sir, you showed it today, na? Like showed the free particle in
hmm,
two-dimensional solution and all.
hmm.
So why after seeing that, I was thinking that what if we, like the solution was like minus h card by 2m, and yeah the the Hamiltonian, and then we had one by r square that is constant,
No, I
like
didn't get
invariant
it.
of.
Which problem are you talking about?
So today the
Let me
free
wait,
part free,
let me
yeah,
share
yes, sir.
the screen.
Can you share it?
Yeah.
Yes, yeah. This one, like minus h card by 2 mu and d square by u by dr square, and the second term, which is
Hmm,
invariant of theta equals to
hmm.
eu. So after that, we see this is what you say. This is a basically a free particle solution. But the thing is
Yes.
that if I just add one more potential, one more external potential, which is Coulombic in nature
Hmm.
and attractive in nature, we can
Yes.
then have a solution for hydrogen atom, right?
That is
Using
what
the
we'll
but
do, right? That is what we'll
okay,
do.
okay,
That is
because
all
that's
we'll do.
okay, that's how we do it in, yeah, like in classical mechanics, that's how we did in using Bernoulli's theorem. We did that for gravitation. So
Yeah.
that's why I was asking, because nowhere
So we
else.
will do this problem here. So we will just, this
Okay,
VR
okay.
will be some, whatever it is, Coulomb potential or whatever.
Yeah, yeah,
Because
yes,
we
yes, sir.
will have this anyways.
Okay, okay. Because yeah, like we didn't, like in any book, even in Griffiths, they didn't do it like the way that you're doing. That's why I'm just
No,
correlating
no,
it
no,
to it.
yeah, of course. The books are. It is hard to get it by reading everything from one book. Yeah, I don't think it any. Maybe Landau. Yeah, Landau does a bit of this kind of. Landau
Land
and
out.
Gunther might have a bit, but again, I generally don't recommend, because this is a very something people don't complained about earlier and people don't like, because it is not easy to look at multiple books unless you have a
Yeah,
very
yeah, yes, sir.
strong
Yes, sir.
command of the subject, because every
Yes,
book
sir.
will introduce a fresh set of notations, and you have to, but if you are confident, just look into that. I think you will find it. Yeah, Landau has this discussion actually. I have the Landau right now in front of me. I think I looked it up in Landau. Then
Because this
I
is
usually forget that why the source, because once I read it and then later I put it up in some way,
this
then I
would be like
forget.
the application of Bernoulli's theorem in quantum mechanics, kind
Yeah,
of.
Barton theory is very generic. Like it is like, you build up the intuition of what is bound state, where the particle is reflecting, and all that, And then now that you have experience of the 1D problem, you can say a lot of things about starting from that. Yeah, I think Landau has a bit of this chapter called motion in a centrally symmetric. Does it have? No, not yeah. I believe it will be hard to read. But if you look at the problems in Landau, oh, Landau has this thing. So problem number 2, problem number 3, and problem number
So
4.
which volume of the series is the quantum mechanical
Yes, the
series,
quantum.
right?
So yeah, Landau has these two potentials.
Okay,
These
okay.
two AR square by BR. I don't know if you can see it.
Yeah, I can see it a
This
bit.
potential and this potential. So they have
What
it.
is the other potential, sir?
You know, A by R square plus B by R and A by R square minus B. So I must have seen
Oh,
it
okay,
in
okay,
Landau
okay.
then. I mean, I didn't like completely imagine it completely. Saw it somewhere. So it
Okay,
must be
okay.
Landau. Yeah, Landau has it. So you look up
Okay,
the
sir.
discussion in Landau. So they have these problems which probably they also solve it partially. So there they give the solutions also, that how to solve these two potentials. Okay, great. Okay, so next week we will do a more formal solution, which is basically the algebraic solution.
Okay.
Okay.
So therefore, this graph that is shown in the, like what you say in your presentation, it won't have a minima in the first quadrant, right? For the second case, a by r square plus b by r.
So this I have to look it up once carefully what Landau had done. I can
Yes,
see that they have this
the minima will be in the second quadrant. Yeah, like yeah,
A
second
by
and
R
third.
square minus B by R.
That's the first case, and plus will have a minima on the other side of the quadrant, not on the positive side of the r.
Oh, you are saying it will be below. Yeah, that is
Yeah,
possible.
yeah,
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 this
yeah,
thing is not
yeah,
like that. This is not
yeah, yeah.
zero.
That, yeah,
This
yes,
is
sir.
not
That,
zero. This is not
yeah,
zero. Some
yeah.
minima. Yeah, so let's not
No, no,
write.
no, no, not minima, sir. No, I'm not saying minima. I'm saying okay. So what I'm saying is in the first case, a by r square minus b by r, the minima is in the first and fourth quadrant,
First and fourth quadrant.
where the value of abscissa is positive.
Oh, you were saying it is fourth quadrant is this.
Yeah,
That
yeah,
this quadrant doesn't matter.
yeah, yeah,
This
yeah.
quadrant doesn't matter because
Exactly,
it is
exactly,
an r greater than zero
exactly,
problem.
sir. Yes, sir. That's what I'm saying. So
So
in
this line is not basically this line is not b equal to zero.
yeah, 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 yeah. No, no, I'm not talking that. I'm taking that in this, the minima is possible with positive values of
Yes.
r. In the second case, the minima is not possible with the positive values of r.
Yeah,
That's what
but
I'm saying.
so the location of minima is not very important here.
Yes,
What
sir,
is
but
important
it
is this
is.
structure. Is this one case allows a bound state, another case doesn't allow a bound state. That is
Yes, sir.
what
So
is
the
important.
second case doesn't allow a bound state, right?
Yes.
Yeah, yeah, yeah. Okay, that's
Right.
what I'm
Yeah.
saying. That's what I'm saying because there is no minima with positive r in the
Yeah.
second case.
Yeah.
Yeah, that's what I was telling in the starting of the class also.
Yeah. So that is what is this. Because the repulsive potential will not allow a bound state. That's the key.
Yes, sir. Yes, sir. It might get into the scattering case.
Yeah. So
Yes, sir.
the generic advice is stare at these problems
Mhm.
and you figure out which allows bound state, which doesn't allow bound state. If it does, you should be able to sketch the solution without actually solving, and qualitatively accurate solution. So that is basically the take home, because as I said, you will definitely forget the formal solution, but these things you will not forget. Okay. Yeah.
Okay, sir. Thank you, sir.
Okay, no problem. Okay, so I close the meeting.